everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering. In this lecture, we'll discuss about the analysis of transistor amplifier circuit using H parameter model. Already we have seen what is H parameter and why we are going for the H parameters. And what is a H parameter equivalent circuit of a transistor? So in this lecture, we'll discuss about the analysis of transistor amplifier using H parameters, and we'll mainly concentrate on the calculation of various parameters, characteristic parameters of amplifier circuit, that is transistor amplifier circuit, like calculation of current gain and input impedance, calculation of voltage gain, and calculation of output admittance, the calculation of overall voltage gain AVS and overall current gain AIS, and also the power gain of amplifier, that is AP. So we'll all see the calculation of all these characteristic parameters by which the amplifier, the performance of amplifier can be analyzed using the hybrid parameter model, that is H parameter model. So before going to the lecture, so first of all we'll see the H parameter equivalent circuit of a general amplifier. So as we all know that the application of transistor is amplifier, so which can be used as an amplifier where the transistor should operate in active region, then only the transistor can be used as an amplifier. So before analyzing the various characteristic parameters of transistor amplifier circuit, we'll just recall what is a H parameter equivalent circuit. So as we all know that the transistor can be approximated as a two-port network, as it is having three terminals. One of the three terminals can be taken as a common terminal between the input as well as the output, whereas among the three terminals, one is taken as the input and the other one is taken as the output, and the remaining terminal is taken as the common terminal between the input and output. So the weak signal is to be applied to the input port and the amplified signal is taken from the output port, right? So here, based on that, we have three different configurations of a transistor. What are the three different configurations? That all we know, that is common base configuration, common emitter configuration, common collector, common base, common emitter, common collector. So what happens in common base? Base is the common, okay, and emitter is input terminal and collector is considered to be output. If you go for common emitter configuration, emitter is the common terminal that is between the input and output, and base is the input and collector is the output, right? Coming to the common collector, collector is common, okay. So as I told you that among the three terminals, we will be taking one terminal as common and one terminal as input and the other terminal as output. So if I take collector as common, base will be the input and emitter will be the output. Okay, so these are the three configurations by which we can approximate the transistor as a two-port network. So now let us see how can we construct a transistor amplifier using transistor circuit. So just take a transistor and connect a voltage source in series with a source resistance Rs at the input side and a load resistor at the output side, so that we can convert a transistor into amplifier circuit. Wherever usually we need to apply the required biasing, that is the DC biasing, such that the emitter to base junction is forward biased and collector to base junction is reverse biased, and some resistors which are used to provide the required biasing and stabilization for the operating point. So that means this is a transistor circuit where we can have DC sources and even resistors also, such that the required biasing for the transistor is provided. As such, the transistor can operate in the active region. And even we need to provide the biasing such that there is a stability for the operating point. That means the operating point should be located in the middle of the load line. Okay, so how can we convert a transistor into amplifier? Just connect a voltage source, AC voltage source in series with a resistance, that is source resistance at the input side and a load resistance at the output side, so that a transistor can be converted into amplifier. As we all know, the equivalent circuit of a two-port network, that is H parameter equivalent circuit of a two-port network. So as I told you that the transistor can be approximated as a two-port network. So just replace the transistor because it is a this is a non-linear device. It is whenever we are going to perform some mathematical analysis, definitely we need to replace the non-linear devices with its equivalent circuit. So that is why we are replacing the transistor with its H parameter equivalent circuit. Okay, so as we have all seen that how to find the equivalent circuit of H parameter equivalent circuit of a two-port network, and I'm telling you that the transistor can be approximated as a two-port network. So I'm just replacing the transistor with its equivalent H parameter circuit. So this is the equivalent H parameter model for the transistor, which can be considered as a two-port network. So this is the H parameter equivalent circuit, which is replacing the transistor. So as we are going for the AC analysis, so definitely the transistor should be replaced with its equivalent circuit because the transistor is non-linear device. So wherever, if you go for even diode also, whenever you are analyzing the circuit, we have to replace the diode with its equivalent circuit. We have seen rectifiers. So in rectifiers, in order to analyze the operation of rectifier, we were replacing the diode with its equivalent circuit even under forward bias and reverse bias. The same way, the transistor should be replaced with its equivalent circuit because it is a non-linear device. So this is the equivalent circuit of a transistor, which is approximated as a two-port network. So what this equivalent circuit consists of? Hi, this is the input impedance in series with a voltage source whose magnitude is HR into V2, where the input port is considered as 1 and 1 dash. Okay, and the voltage at that input port is considered as V1, and the current flowing through that input port input loop is represented with I1. And similarly, output port is nothing but a circuit which is obeying the KCL. That means all the elements will be connected in parallel. So this is the output circuit, output equivalent circuit. So here all the elements are connected in parallel. What are the elements that are connected in parallel here? It is a dependent current source whose magnitude is HF into I1, where HF is the forward current gain and HR is the reverse voltage gain. And I1 is the input current and HO is the output admittance. And as we are considering that this is a output port, output equivalent circuit, so the current flowing through the output circuit is I2 and the voltage across this output port is considered to be V2. And the port is represented with 2 and 2 dash. Okay, so this is the equivalent circuit, H parameter equivalent circuit of the transistor. So to which we are connecting a voltage source in series with a source resistance at the input side and a load resistance at the output side. Let us consider the current flowing through the load resistor as IL. So where if you see this, I2 and IL are opposite to each other, where I2 is flowing in this direction, IL is flowing in this direction. That means it is leaving the node 2. So here, that is why we can say that IL is equals to minus I2, or else I2 is equals to minus IL. So this we have to remember. So this is the equivalent H parameter equivalent circuit of the transistor amplifier circuit. Okay. So now we are going to calculate all the characteristic parameters of amplifier circuit using this hybrid parameter model. Now first let us see. So before that, so this equivalent circuit is valid for all the three configurations of transistor. Only the thing is we are going to append one more subscript to all the H parameters based on the configuration. If it is common base configuration, we will be representing H parameters with one more suffix added, that is HIB, HRB, HFB and HOB. So these are the H parameters for common base configuration. If it is common emitter configuration, HIE, that means the suffix E is added and the parameters will be HRE, HFE and HOE. If it is common collector, HIC, HRC, HFC and HOC. That means, or what I want to say, this circuit is valid for all the three configurations of the transistor. Only the thing is, we need to add one more suffix to the H parameters representing the configuration of the transistor. If it is common base, add B to the H parameters as a suffix. If it is common emitter, add E. If it is common collector, add C. So these are the equal H parameter equivalent circuits of common base, common collector and common emitter configurations. Okay, so here, as we all know that this is a common emitter configuration. So we know that base is the input terminal, emitter is a common terminal and collector is the output terminal. So where the input parameters are IB, VB and the output parameters are IC and VC. In short, we are calling. And coming to the equivalent circuit here, the equivalent circuit of the transistor under common emitter configuration is represented with HIE, HREVC. Okay, so HREVC and the current flowing is IB and the voltage drop across these input terminals is VB. So here the input terminal is B, whereas the collector common terminal is emitter. So emitter is a common terminal which is to be grounded. And output terminal is collector and the common terminal is emitter, right? That means emitter is common for both input and output. And here the current source. So HFE into input current. What is the input current we have? IB. So HFE into IB. And the output admittance, HOE. And the current flowing through the output terminal is IC. So these are the equations. VB is equals to HIE. So what are the equations we have? V1 is equals to HI into I1 plus HR into V2. So actually in common emitter configuration, V1 is VB and I1 is IB, right? Similarly, V2 is VC and I2 is IC. Just substitute these values. And one more equations we have, I2 is equals to HF into I1 plus HR into, HO into V2. Okay, so HF, so I2, that is V1 is input voltage VB, so HIE into input current IB plus HRE into output voltage VC. Similarly, I2 can be, this equation can be modified for the common emitter configuration as this. So I2 is IC, so IC is equals to HFE into IB plus HOE into VC. Similar way, these are the equivalent circuits of transistor in common collector and common emitter common base configurations. Okay, so now we are going to find out the current gain of the transistor, generalized transistor. Okay, I'm not considering any of the configuration. I just want to derive all the characteristic parameters for a generalized transistor amplifier using H parameter model. Okay, so where these all the formulas, whatever I am going to derive now, will be applicable for any of the three configurations. Okay, so that is why I am specifically mentioning that it is the generalized analysis of transistor amplifier using H parameter model. So now, first of all, current gain. We can also call it as current amplification factor. Current gain, or else we can also call it as current amplification factor. Okay, current amplification factor, right? So, how can we define the current gain? First of all, we all know that gain is a parameter which is calculated from output to the input, right? So, as we are saying that it is current gain, so it is defined as a ratio of output current to the input current. So here, this is a generalized circuit. So that is why the output current is considered as I2, whereas the input current is considered as I1. Okay. So before that, here always you remember the output voltage is always measured across the load resistor. So that is why the current that is flowing through the load resistor is always considered as the output current, and hence the current gain is defined as a ratio of output current IL to the input current, where input current is I1. So IL by I1. And as I already told you that IL and I2 are opposite directions. So that is why we can say that both are equal in magnitude, but those are opposite. So that is why we can say that IL is equals to minus I2. So I can substitute this one in this equation. So AI now becomes minus I2 by I1. Now I want to derive a mathematical expression for current gain in terms of H parameters using this one, right? So for that, what I'm doing, we have the equation, output equation, that is I2 is equals to HF into I1 plus HO into V2. HF into I1 plus HO into V2, right? So now here what I want to do is, I want to substitute. What is V2? V2 is the voltage drop across the load resistor. So the voltage drop across the load resistor is measured across the port 2 and 2'. So that is given by, as we know the current flowing and the resistance, so we can find out V2, that is equals to IL into RL, or else we can also write it as minus I2 into RL. Minus I2 into RL. So here what I can do, I2 is equals to HF into I1 plus HO into V2 value, I can write it as minus I2 into RL. So now take this side. So I2, if it is minus, so if it comes this side, then it becomes plus HO into RL into I2 is equals to HF into I1. Okay. So now here, now I2 is equals to, I2 into 1 plus HO into RL is equals to HF into I1 into HF into I1, right? So now here what I am doing, I want to have a relation, that is I2 by I1. I2 by I1, so that can be given by HF divided by, so I am taking this taking this term this side and this I1 this side. So I2 by I1 is equals to HF by 1 plus HO into RL. HF by 1 plus HO into RL. And we already know that the current gain is given by minus I2 by I1, which is equals to, we already found the value of I2 by I1, which is minus HF by 1 plus HO into RL. This is the formula for current gain. This is the formula for current gain. Okay. So like that, we can have an equation for current gain of the transistor amplifier using H parameter, and the formula is given by minus HF by 1 plus HO into RL. So this is current gain. And now we can also find out one more parameter, that is input impedance. Impedance is always defined as a ratio of voltage to the current, right? So input impedance. So whenever you are looking into the input port, so that is 1 and 1 dash, the impedance seen when we are looking into the port 1 and 1 dash is defined as the input impedance. So that means whenever we are looking into the input port, then whatever the impedance that we can see is known as input impedance. So you may think that RS is there. This is also input resistance. So this is the internal resistance of the source. So I am not taking this RS into consideration. Only the input impedance is defined as the impedance seen when we are looking into the port 1 and 1 dash as the input impedance. So here, when I look into this port 1 and 1 dash, what is the input voltage and input current that I can see? Input voltage is V1 and the input current is I1. So that is why the input impedance is defined as a ratio of input voltage V1 to the input current I1. So that is why I can write the formula for Zi, that is the input impedance, as V1 by I1. Now I want to derive the equation for this input impedance. So for that, what we need to consider? So as it is related to the input port, now consider the equivalent equation, that is the equation for the input loop. So that is this one. So what is the equation we have? V1 is equals to Hi into I1 plus HR into V2. HR into V2. This is the equation we have. Now we already know that ZI input impedance V1 divided by I1. As we all know that V1 is HI into I1 plus HR into V2 divided by I1, right? Now expand this one. So HI into I1 divided by I1 plus HR into V2 divided by I1. So this one get cancelled. So HI plus HR into V2 by I1. So in order to calculate this ZI, we need to find out this ratio. What is this ratio? V2 by I1. Okay. So for calculating this V2 by I1, so what should we consider? So for calculating this, we have to consider, for calculating this, we need to consider the output voltage equation. What is the output voltage equation? V2 is equals to IL into RL, or else we can also write it as minus I2 into RL, right? Minus I2 into RL. So here we can also from the current gain formula, that is AI is equals to minus I2 by I1. So from this one I can write minus I2 as what I can write minus I2 as AI into I1. Just substitute this one in the above equation. So now V2 can become AI into I1 into RL. AI into I1 into RL, right? Just substitute. So from this one, I can find out the ratio V2 divided by I1 is equals to AI into RL. AI into RL. So now substitute this one in this equation. Now ZI becomes what? HI plus HR into AI into RL. AI into RL. So we already know the value of AI. What is AI? Minus HF by 1 plus HO into RL. So ZI is equals to HI plus HR into RL. So AI can be written as minus HF by 1 plus HO into RL. Sorry, 1 plus HO into RL. So now I can write this equation as HI minus HF into HR divided by 1 plus HO into RL into RL, right? So this is the equation. Now what I'm doing, I'm taking in the denominator, I'm taking RL as common. So ZI is equals to HI minus HF into HR divided by RL. So if I take RL as common, then it becomes HO plus 1 by RL into RL. So this RL get cancelled. So inverse of input resistance is nothing but impedance. So inverse of resistance is nothing but admittance. So here I can write this one as YL. I can write this one as 1 by RL as 1 by YL. So I can write the formula for input impedance as HI minus HF HR divided by HO plus YL. HO plus YL. So this is the formula for ZI. Okay. So the formula for ZI is HI minus HF HR divided by HO plus YL. Okay. HO plus YL, where YL is equals to, where YL is equals to 1 by RL. So this is the formula for input impedance. So input impedance of an amplifier circuit is given by HI minus HF HR divided by HO plus YL. Now coming to the voltage gain. So how can we find out the voltage gain? So how can we define the voltage gain first of all? So voltage gain is defined as a ratio of output voltage to the input voltage, and it is given by, so we all know that output voltage is V2 and the input voltage is V1. So AV is equals to V2 by V1. AV is equals to V2 by V1. So here now as AB is okay. So here as V2 is equals to, we all know that minus I2 into RL, minus I2 into RL. So I can substitute AV is equals to, and we can also substitute minus I2 as AI into I1 into RL. Okay, because minus I2 can be written as AI into I1. So I just substituted there. Now I'm going to substitute this V2 in the above equation. So what I'll get? AI into I1 into RL divided by V1. So we all know that Zi is equals to V1 divided by I1. So now substitute this one in this equation. So what I'll get? AI. So this I can write it as 1 by Zi. So AI into RL by Zi. So this is the equation for voltage gain. So the voltage gain of an amplifier is given by AI into RL by Zi, where RL is the load resistance or load impedance and Zi is the input impedance. So we have already derived the formula. What is the formula for Zi? Hi minus HF HR by 1 plus HO into YL. So that is a formula for Zi, and RL is the load resistance. Okay, so this is the formula for AV, that is voltage gain, which is defined as a ratio of output voltage to the input voltage. Now let us go for the another parameter, which is output admittance. The output admittance, why not? Basically can be obtained by making Vs to 0 and the load resistance, that is ZL or RL, to infinity. So in order to find out why not, first set the value of Vs to 0 and RL to infinity. And now drive the output terminals from a generator V2. So what we are doing, this is the procedure. So what we are doing, we have to make Vs to 0 and we have to make RL infinite. Making RL infinite means what? Open circuiting. So then it becomes generator. It is driving the circuit now. Okay, if it is driving the circuit, then the output admittance, if it is driving, then what is the current flowing through this? That is I2. And here the output admittance can be defined as a ratio of output current to the output voltage. So that is Y0 is equals to I2 V2 by setting Vs to 0 and RL to infinity. Making RL to infinite means making the input open, making that output port open circuited. And considering that V2 is driving the circuit, that means V2 acts as the input voltage. So now here in this case, how to find out the output admittance? So in order to find out the output admittance, so what we need to consider? So we have the equation. What is that equation? I2 equation. So I2 equation is HF into I1 plus HO into V2. HO into V2, right? So now divide this equation by V2 on both sides. So divide the equation by V2 on both sides. V2 on both sides. So I'm dividing this equation by V2 on both sides. So I2 divided by V2, then HF into I1 divided by V2, it becomes plus HO into V2 by V2. This one get cancelled. Okay. So, okay. If it is cancelled, then what the remaining thing we have here? I2 by V2, which can be given by Y0 HF into I1 by V2 plus HO. Now what we need to do? We need to calculate this value, I1 by V2. So how to calculate this I1 by V2? Okay. So here we have what we are doing, we are making Vs 0. If we are making Vs 0, then what happens? This will be not there. So this will be directly connected here. So that means RS will be now connected in series with this. So if as we all know that in series the current flowing will be same. So what is the current flowing in this? That is I1. So the same current will also flow through the resistance RS, because we have made Vs 0. So that means it is short circuited. If it is short circuited, RS will now be connected in series with the resistance Hi, and hence the same current I1 will be flowing through it. Now apply the KVL here. Making Vs 0, apply the KVL to the input loop. Then it becomes Rs into I1 plus Hi into I1 plus HRV2 is equals to 0, because we made Vs is equals to 0, right? So this is the equation. So now take this HR that side. So and take I1 as common in this too. So Rs plus Hi is equals to minus HR into V2. So now I want to find out the value of I1 by V2. So just send this Rs plus Hi this side and V2 this side. So what it becomes? Minus HR by Rs plus Hi. Rs plus Hi. So we found the value of I1 by I2. Now substitute this one in this equation. Substitute this I1 by I2 in this equation. So then I2 by V2, which is nothing but Y0, is given by HF into I1 by V2 value we have just found, right? Minus HR by Rs plus Hi, Rs plus Hi plus HO, right? So now I can write this Y0 value as HO minus HF into HR divided by Rs plus Hi. So this is the formula for output admittance. HO minus HF HR by Rs plus Hi. That means we can say that the Y0, the output admittance, purely depends on Rs, because all these are the H parameters. These are the constants for each and every transistor. That means Y0 value purely depends on Rs. Okay. So this is the output admittance equation. HO minus HFHR by Rs plus Hi. So that is output admittance. So when we are calculating the output admittance, we should keep in mind that make Vs is equals to 0 and RL to infinite. Okay. And by considering RL as infinite, now V2 will drive the circuit because we made Vs 0. Okay. Now voltage amplifier. So we till now we have find the voltage gain and current gain, but in both the cases we were neglecting the voltage source. But the gain which is calculated by taking the voltage source Vs into effect is called as overall voltage gain. So that is now we are finding now. So the amplification factor AVS by taking into account the source resistance Rs of the source. Okay. So that means while calculating AV and AI, we have just neglected Vs and Rs. Now by taking into effect, that is account the Vs and Rs, we are going to calculate the voltage gain, and that voltage gain is called as overall voltage gain. And that overall voltage gain, as now we are considering this Vs into effect, now the voltage, this will act as the input, and hence instead of V1, Vs will now act as input voltage, whereas the output voltage remains same, that is V2. So V2 divided by Vs is the overall voltage gain, where overall voltage gain is represented with AVS. So here now what I am doing is I'm just modifying this one by just multiplying and dividing this by V2 by Vs into V1 by V1. So that there is no difference if I multiply and divide this one by V1. So and now I'm rearranging the terms here. So how I'm rearranging the terms? V1 divided by Vs into V2 divided by V1. We already know that V2 by V1 is nothing but AV. So V1 divided by Vs into AV. So AV is the voltage gain without taking the Vs into effect. So now we need to find out V1 divided by Vs. So for that, we have to consider the equivalent circuit of this one. So as you already know that whenever we are looking into the port 1 and 1 dash, the input impedance C is represented with Zi. So now I am replacing this entire circuit with its equivalent impedance Zi. Okay. So now the equivalent circuit will be, that means I am replacing this equivalent circuit of the input by considering the input impedance into consideration. So then it becomes RS and this is Vs. Just a second. Okay. Just a second. Okay. This is RS. Okay. Vs or else RS and this is Zi. So what is the voltage across this one? This is 1 dash and the voltage across this one is V1 and this is RS. This is RS. So this is just like a potential divider. Potential divider circuit means these two elements are connected in series. In series, current will be same and the voltage will be getting divided. So that is why this circuit is called as potential divider circuit. Now apply the potential divider principle and calculate the value of V1. What is V1? V1 is the voltage drop across the input impedance, that is Zi. So according to the voltage divider principle, so we can have the value of V1 as, so the value of V1 can be given by the input voltage Vs into that resistance. What is that resistance? Across which the voltage drop V1 is there, that is Zi divided by total resistance. What is the total resistance? Zi plus total. How many resistances are connected here? 2 resistances, that is Rs and Zi. So Rs plus Zi. Rs plus Zi. So that is V1 according to the potential divider principle. So the voltage drop across any resistance is given by the input voltage into that resistance divided by the total resistance. So that resistance is Zi because I am finding out V1, where V1 is the voltage drop across Zi. So V1 into Zi divided by Zi plus Rs. So now from this one, I can calculate V1 by Vs, which is equals to Zi divided by Zi plus Rs. Now substitute this one in the above equation. So now AVS can be obtained as AV into Zi divided by Zi plus Rs. Zi plus Rs. Okay. So here now we already know that AV is equals to AI into RL divided by Zi. Just substitute this in the above equation. So now AVS can be obtained as, since, okay, so AI into RL, or else we can also represent it as ZL divided by Zi into Zi by Zi plus Rs. So this one get cancelled. So now the equation for AVS is given by AI into RL divided by Zi plus Rs. Zi plus Rs. This is the equation for overall voltage gain. So now if Rs is equals to 0, then what we will get? AVS is equals to AI into RL divided by Zi. So that is equals to AV, right? So that means if Rs is equals to 0, it represents the voltage gain without considering the Rs into effect. So this is the overall voltage gain or else voltage amplification factor by taking the voltage source into consideration. Where while calculating AV, we did not take any voltage source into consideration. Now similar fashion, we are now going to find out the overall current amplification factor, or else the current amplification factor by taking into account the source resistance. Okay. So now in the previous case, while we are finding out the voltage equivalent overall voltage gain, we have replaced that input circuit with Thevenin's equivalent circuit. What the Thevenin's theorem states, a voltage series will always be connected in voltage source will always be connected in series with a resistance. So now what we need to do? We need to replace the same input circuit by using Norton's theorem. Okay, so we have to replace the input by Norton's equivalent circuit. What is a Norton's theorem states? The current source always will be connected in parallel with a resistance. So now I am going to replace this circuit with its equivalent, Norton's equivalent circuit. So how can we replace that? So Vs I am going to convert it into current source. So which is Is. So this is Is. Now this Rs now will be connected in parallel, whereas anyhow this is replaced with Zi. So we have Zi here, and here the current flowing is I1. This is Rs. Okay, so this is the Norton's equivalent circuit for the input circuit. Okay, so always you remember Norton's equivalent circuit consists of resistance in parallel with a current source. Now here, before this, just I am again multiplying and dividing this one by I1. So now I am rearranging the terms, minus I2 by I1 into I1 by Is. So what is minus I2 by I1? Minus I2 by I1 is always AI, and I1 by Is. That means in order to find out AIS, I have to find I1 by Is. Now this is nothing but a current divider circuit. So why? Because all the resistors are connected in parallel. So in parallel voltage is same, only the current will be getting divided. So now this is a current divider circuit. Now apply the current divider principle, and now I want to find out I1. What is I1? I1 is a current flowing through Zi. So according to the current divider principle, the current through a resistance is equals to the input current into the opposite resistance divided by the total resistance. What is the opposite resistance to Zi? Rs is the opposite resistance. So Is is the input current into opposite resistance is Rs divided by total resistance is Rs plus Zi. So now from this one I can calculate I1 by Is, which is equals to Rs divided by Rs plus Zi. So now AIS can be given by AI into Rs divided by Rs plus Zi. So this is the equation for overall current gain. That is, by considering the voltage that is a resistance, source resistance into effect, the overall current gain formula is given by AI into Rs by Rs plus Zi. Now we want to have a relation between AVS and AIS. AVS and AIS. So for that, consider the equation, that is AVS is equals to, let us try to see the equation. AVS is equals to AI into RL by Zi plus Rs. This is the equation. I want to consider this one. So AI into RL divided by Rs plus Zi. So I am just multiplying and dividing this one by Rs. So I am just multiplying and dividing this one by Rs. So now AI into Rs divided by Rs plus Zi into RL by Rs. Right? So now what is this one? According to the previous AI into Rs by Rs plus Zi is nothing but AIS. So AIS into RL by Rs. So this is the formula for AVS in terms of AIS. So we can also write this one as, so wherever we have RL, we can simply write ZL divided by Rs. So AVS and AS. This is a relation between the overall voltage gain and the overall current gain. So now let us find out the last parameter, which is the power gain. So gain, as we all know that It is defined as a ratio of output to the input. As we are calculating the power gain, we need to consider it as a ratio of output power to the input power. So output power is represented with P2 and input power is represented with P1, where P2 is the output power which is measured across a load resistor. So it is always, you know, that power is equals to V into I. Power is equals to V into I minus V2 into IL. Minus V2 into IL, or sorry, minus V2 into I2. Okay. Now P1 is nothing but the input power which is given by V1 into, why we have taken minus V2? Because V2 into IL is the output power, whereas IL is equals to minus I2. So that is why we have written it as minus V2 by I2. So now the power gain is calculated as minus V2 into I2 by V1 into I1. So V2 by V1 is nothing but voltage gain AV, whereas minus I2 by I1 is nothing but AI. So that is power gain is equal to the product of voltage gain and power gain. Okay, equal to the product of voltage gain and power gain. So AP is equals to AV. What is AV? AI into RL divided by ZI. Right? So now we are substituting that AI into RL divided by ZI into AI. So I can write this one as AI square into RL by ZI. So this is the formula for power gain. Okay. So this is the formula for power gain. So these are all the characteristic parameters of transistor amplifier which are calculated using the hybrid parameter model. So now list of all the formulae which we have derived till now. So what is the current gain? First parameter we have derived is current gain minus HF by 1 plus HO into RL. And the next parameter input impedance, that is equals to HI minus HF HR divided by HO plus YN. Just we'll have a look about the formula of input impedance. Just I'm going to confirming HI minus HF HR by HO plus YN. And coming to the voltage gain, AI into RL by ZI. Okay. So next, the current gain voltage gain AI into RL divided by ZI. This is another formula. And now coming to Y naught, already we have derived Y naught HO. Okay. HO. Just have a look. So we need to remember all this HO minus HF HR by RS plus HI. HO minus HF HR divided by RS plus HO. Okay. RS plus HI. RS plus HI. Sorry. RS plus HI. And now coming to the AVS. What is the formula of AVS we have got? AVS is equals to AVS is equals to AIS into RL by RS. AVS is equals to AI into RL by RS plus ZI. AI into RL by RS plus ZI. Similarly, AIS is equals to AI into RL divided by RS plus ZI. This is RL, this is RS. This is RL, this is RS. And similarly, the power gain is AP into AI. AP into AI. These are all the formulas which we have derived. Okay, so these are the formulas which will be applicable for any of the transistor amplifier, that is either common base amplifier or common emitter amplifier or common collector amplifier. So only the difference is the H parameter values will be changing. So what I want to say, whatever the analysis we have done is applicable for any of the three configurations of the transistor. So these are the H parameter values for all the three of a transistor in all the three configurations. So HI, HR, HF, HO, and these are the three configurations. So the thing is, I wanted to say the analysis of transistor amplifier using hybrid parameter model is same for all the three configurations of. That means this analysis is analysis holds good for common base amplifier, common emitter amplifier, and common collector amplifier. Only the thing is the H parameter values will be changing. Based on the H parameter values, all the characteristic parameter values will also change. Okay, so this is about the analysis of transistor amplifier using hybrid parameter model. So the thing is, we have to remember all the formulae which we have derived till now, and these H parameter values, these are the typical values of H parameters for all the three configurations of a transistor. So these typical values are also should be memorized in order to solve the numericals on the transistor analysis. Okay, so that's all for this lecture. I hope it is clear to you all. If you have any queries, you can just post it in the comment section. Thank you one and all.
Like, share and subscribe. Hit the bell icon for more updates.